Okay, so this is being recorded and I'm sharing the screen. Okay, let me move this out of the way. Okay, so when we left off last week, we were talking about the size of the atom versus the size of the ion. And the bottom line, as we talked about this last week, the negative ion, the anion, is larger than the atom and cation. And that's because the majority of the size of the atom is usually electrons. It's occupied by electrons. And it was the scientist Rutherford who came up with that information. In his experiment, when he was discussing the nuclear model of the atom, he said the atom is mostly composed of empty space occupied by the electrons. So if you have more electrons, we generally assume the size of the atom is larger. That's why it has more electrons. So remember, the anion is the chemical species that has not only its original electrons, it has additional electrons, making it extra large compared to the cation. Okay, now we're moving on and talking about another periodic trend, and this periodic trend is called ionization energy. In ionization energy, what we're looking at here is we're trying to remove an electron from an atom. Okay, so we'll start with ionization energy, the definition. We're told, now once again, when it comes to definition with chemistry, I usually personally attach it to purpose or an activity that we'll be doing in labs to make it more relatable. This is the minimum energy needed to remove an electron from an atom or ion in gas phase. So we're being told ionization energy is the minimum amount of energy. That means that if you're trying to remove an electron, there is some kind of requirement, a prerequisite, right? That prerequisite here is that minimum amount of energy that must be applied to the atom to remove the electron. And our goal here is to remove the electron. And then we're being told in order to remove the electron from any chemical species, that chemical, either the atom or the ion, has to be in gas phase. Okay? So you cannot remove an electron from a metal in a solid state. To get the electron to come out, we tend to make sure whatever you're trying to ionize is already in gas phase, and then you remove the electron. Okay, since you, the scientists, are adding energy to that gas phase chemical, either atom or ion, when we add energy, that's called endothermic. This definition, endothermic or exothermic, is always from the point of view of the chemical. So when we are adding energy to the process, the chemical is receiving energy, right? And so this is endothermic. Energy is coming into the chemical. So we're told here this requires input of energy to remove the electron. Okay, then we're told here the valence electron is the easiest to remove. So once again, when I was learning this, we're learning this right about, when I look at my past, about middle school level. So middle school is when I'm beginning to, I get friends and super distracted, right? Oh, I would say worst time of your life to learn this, but they wanted us to learn this when we were young. So by the time we got to high school, we were familiar with this and we're not learning it for the first time. So I'm trying to conceptualize this in my head, and I'm like, okay, what's valence electron again? So imagine you're trying to remove the electron from the different energy levels, right? So to show the energy levels, I'm going to show them as whole, but I'm going to use Bohr's model because I think I mentioned this before, right? We tend to go back to Bohr's model, the model where the energy levels are complete and whole and not broken apart, because it's the easiest to use to explain what's going on. Even though when we go to the actual quantum model, we actually break those energy levels apart into sublevels. So you will see me most of the time go back to Bohr's model as I explain new concepts, right? We have the nucleus that's positive, you have the different energy levels. And once again, in my head, I visualize the concert hall where the stage is in the middle and the concert hall is circular, right? So you have the valence selection, the one that's very close to the edge. It's easier to remove, okay? That's what they're saying. This electron is a lot easier to remove than the one that's very close to the nucleus. So let's talk about this. Remember that all of these electrons are technically being held in space in their orbit according to Bohr's model, right? Or in that energy level according to the quantum mechanical model by the attraction they feel from the nucleus. We talked about this on Friday in more detail that the first electron, the one in the innermost energy level, N1, experiences the full nucleus, nothing hinders it. Electron on energy level 2 experiences an effective nuclear charge because the electron in front of it is kind of masking some of the charge from the nucleus. Same thing with 3, and then this last one, N is 4, right? Remember, the energy levels go up to 7. So the electron that's furthest from the nucleus is experiencing the least attraction from the nucleus because this electron here is being shielded, or the nucleus is being masked by 1, 2, 3 electron, 3 electrons. So this electron out here is experiences the least nuclear charge, and therefore it experiences the least force of attraction. So if you as a scientist is trying to remove the electron, any electron from the atom, and you want to be successful, you want to go for the easiest one. The easiest one to remove is the valence electron. Okay? The valence electron is the easiest to remove. It requires the lowest amount of ionization energy. So here we have what is called the first ionization energy. The first time you're planning to remove the electron. First time ever. So this means this is the energy to remove electrons from the neutral atom. So this atom has not lost electrons yet. This is the first time that you are attempting to remove electrons. So we're told here, all atoms have a first ionization energy. So they're showing you the equation here. This is the atom, and the atom has a symbol M. This is a generic symbol. Instead of X, they use M. They use M because metals are the ones that lose electrons. So M here stands for some metal, whatever the metal is. And then you're adding the first ionization energy to that metal, and your goal is to remove, this is the first electron. Okay, so once you remove the electron, the metal that used to be an atom is now an ion. Okay, remember, atoms have not lost any electrons. Ions are what remains after electrons have been lost. Okay, now we're told here this is second ionization energy. In this case here, you didn't just remove the first electron. Now you're going back to the ion, and your goal is to remove the second electron. Okay, now it gets complicated. Okay. In this scenario, this first electron and its energy level is gone. But this is the same atom that you already removed the first electron from. So when I was learning this years ago, the rationale I came up with is the ion has learned. Okay, it's realized that when you show up, you're about to remove electrons, so it becomes a little smarter. Now, in reality, that's not what happens. Okay, but the second electron you're trying to remove is a lot closer to the nucleus. That's the reality, right? It's a lot closer to the nucleus, and it has a greater attraction because it experiences a much greater nuclear charge from the nucleus. For that reason, you are now competing, like you did with the first time, with the nucleus to remove the electron. The nucleus is holding on stronger to the second electron, this one right here. So you would have to apply even more energy to remove that electron. So yeah, here we have the second ionization energy. And in the end, the second ionization energy is bigger than the first ionization energy because electron is closer to nucleus. Okay. The second electron you're trying to remove, It's closer to nucleus. So I'll just tell you a little story. Now, I'm giving you a more sophisticated version of what I was learning. Now, I was in middle school, okay? I'm trying to relate this to my life. And I was like, what in my life reminds me of this scenario right here? I didn't know that saying of you fool me once, whatever, shame on me, or shame on you, fool me twice, shame on me, something like that. I didn't know that this is me in Africa, not in America. So what I thought about was, you remember when we were kids, we used to, I don't know why we're bad kids. We try to take the little chicks from the chickens, and it was a game. I never tried that, but I watched it happen. Okay, I never tried it. And when you got one of the chicks from the chickens and you ran away, the mother hen got very protective of the remaining chickens, the little chicklets that it had, and it actually pulled them closer, right? So I remember that happening, thinking that's a very interesting defense mechanism versus my friends are bad and we are bad, right? Anyway, so it was a lot harder to pull another chicken from her because she learned what you were trying to do. So somehow in my head, I related that experience to this, right? When you try to remove the second electron, it's even harder. And the more electrons you try to remove, it gets harder and harder and harder. So even though this part was conceptually a little harder for me to grasp, I tied this to that life experience and it helped me navigate through these, you know, this information. So they show you right here the amount of energy required to remove the different number of electrons in the same element. Now for this graph here, it's showing you only the first ionization energies for different elements. So let me see. This first one is showing you helium, and I'm assuming this is hydrogen. So this is hydrogen right here. So this is the first period. The second one is period 2 from lithium all the way to neon. So you can see it's not really a straight line. You think it would be a straight line, right? It's staggered. So we're about to see why going from left to right in the periodic table, you don't have a smooth straight line. It's a lot deeper because remember, even though we're drawing the energy levels like this, in reality, they're not round and complete like Bohr said, right? So all the things that Bohr said that we use to explain stuff becomes a reality when we're actually looking at experimental results. So right here, we don't have a simple straight line. Even though, yeah, when we go from left to right, the energy level increases, it staggers. Sometimes it drops, sometimes it goes up, kind of like stock, right? So let's see why. We're told here generically, I've already explained these two right here. You can go ahead and read over that. The first ionization energy decreases down the group, and they're telling you why. The valence electron is further away from the nucleus. First ionization energy increases across the period. Effective nuclear charge increases. Okay, so generically, this is how I visualize it. The size of atom is inversely proportional to ionization energy. Okay, what does this mean? This means the larger the atom, the lower the ionization energy. Okay, that's the bottom line. The smaller the atom, the larger the ionization energy. Okay, this is the meaning or the implication. Okay, my handwriting is horrible this morning. But yeah, that's the implication. This is how it plays out when you're looking at the periodic table. So what I do is I look back at what I understand because I was trying to memorize this once again because if you take chemistry as your major, you get the rhythm of how the class is taught and where it goes. And this is one of those things you have to know, periodic trends. How does the size of the atom change from left to right, from top to bottom? How does ionization change from left to right, from top to bottom, right? You get used to that. Junior level, same thing. Grad school, Same thing, right? So when you major in something, you get to hear the same information over and over again. It gets deeper each time, but then you get used to what comes next, right? So what I did then was relate ionization energy to size. So I'm going to be showing that to you right here. Once again, my mock periodic table. In my periodic table, I keep it simple. Usually I just have fluorine on the top right corner. And then I have what? Where's my periodic table? Cesium. You can put francium here. Cesium is technically the largest, but yeah, you can put that there. That works. Okay, remember we talked about this before. Fluorine was the smallest, right? So going back to atomic size, smallest in the size. And then cesium, which is next to francium, is the largest. Okay, as far as size is concerned. So we're told here the ionization energy is opposite. So if you're trying to get an electron from a very, very small atom, let's think small atom. So if atom is smallest, then it should have the highest ionization energy, right? Because they're kind of opposite to each other. The trend is opposite. Smallest atom goes with the higher ionization energy. Then down here, if we have the largest size of the atom, then this goes with, well, I should have written differently, highest ionization energy. Okay, so of course, if you're going from left to right, you know what is increasing. If you go from top to bottom, you know what's increasing, right? So from left to right, as far as ionization energy is concerned, ionization energy increases, right? This has to increase. So by the time we get to fluorine, fluorine will have will be the highest, right? When we go from top to bottom, we have to end up with, oh, sorry, it's supposed to be lowest. It's the opposite trend. I wrote here largest and then lowest, right? This is the opposite trend. So by the time we get to the bottom, we should have the lowest ionization energy on the bottom. So then ionization energy will decrease, right? As you go down, it gets smaller and smaller and smaller. So what's the rationale? This is very tiny. This is huge, humongous. It boils down to how strongly the outer electron is being held. In a small, stingy atom like fluorine, I'll say this is the nucleus. This is positive, right? The outermost electron is not that far from the nucleus because the atom is so small. It's so tiny already to begin with. It's the smallest ever, the smallest atom we have. So the valence electron for fluorine. It's not fluorine. I have to call it, I would say fluorine, but I would write it fluorine. No, it's fluorine. Is very close to the nucleus, right? Because the atom is very small. On the other hand, yeah, this is exaggerated on purpose. The valence electron for francium is very, very far from the nucleus relatively, right? You can even speak, I can even draw an arrow here. So valence electron is far from nucleus. So you can see, remember, the nucleus is the one that's holding the valence electron in place. It's preventing it from just going off and leaving. So when we are trying to remove electron, we are really competing with the nucleus. Since this small atom here, the nucleus is so strong, it's not just holding the valence electron, but holding everything else. It's harder to remove. So I'll say here, harder to remove electron because the nuclear charge here is very high. This one here, easier to remove electron. The electron is very, very far from the nucleus, okay? So the size here determines the other trends too. The size makes a difference in the behavior, okay? So for that reason, we see, it shows you right here, going from left to right, you have increasing ionization energy because the size decreases. And the trend kind of goes from left to right like this. Group 8 is always the exception. Group 8, we don't even use that. Group 8 in trend is an exception. Okay, we generally don't use group 8 that much in periodic trends because it doesn't really follow the trend. But if you're looking at group 8 alone, do you see how much high, like from left to right, it kind of decreased, right? Then when you got to group 8, the green part here, I don't know if you can see green, it's really high. So group 8, remember, they were the ones that were inert, they don't react with the other elements. So group 8 has a much, much higher ionization energy. So can you make it react? Yeah. Will it cost you? It will cost you a lot in energy because they're so stable. And when they're stable, the elements themselves have a lower energy. So when you're trying to remove an electron from it, you will pay with energy. Okay. The currency in chemistry is energy. Okay. So even though we don't have a question here, I thought we had a question because this is going straight to metallic. Oh, this I just realized this is supposed to be ionization energy. I'm like, why is it saying right? Ionization energy. We're doing metallic last. Okay. Just like we did before. On the basis of periodic trend, determine which element in each pair provided, right, has a higher first ionization energy. So we are just comparing ionization energy. So just like before, they're giving us this list. Let me go ahead and erase that. I'll copy this over, add a new page, and then we'll go from there. Copy this. Okay, let's see. Is that page on here? Okay. So we're supposed to look at periodic trends, right? Just like before. You draw your little table. You don't have to do it this way. I just like the visual. It helps me be focused and it helps me work out more complex problems. On the basis of periodic trends, okay, I have my periodic table here. Determine which element in each pair has a higher. So we're looking for the higher first ionization energy, aka what we're looking for is the smaller atom. See, I am more comfortable with this atomic size than the ionization energy, so we'll go with that. Okay, so let's see, aluminum and sulfur. With this one here, once again, you need your real periodic table so you can just compare the two, right? I'm going to just write the relative positions here. Aluminum, sulfur, they have a side by side role relationship or period, a cross relationship, right? So remember, going from left to right, ionization energy increases, right? I mean, and then from top to bottom, ionization energy decreases. I put here DEC. Okay, so from left to right, it's asking which one is higher. So by virtue of the positions, that will be sulfur, correct? So sulfur should be higher. It's further right. The size is smaller, right? Okay, what's next? AS and SB. Oh, okay, we can do that. So I'm done with this one here. I'll erase this. You see how I have the little arrows to help me there? AS and SB. So AS and SB, see, oh, they want higher. So if we're going down, the size is getting bigger and the ionization energy is increasing. So we want the opposite, which is the one that's further up, which is smaller, right? That should be AS. Okay, what about N and SI? I don't know if you guys are noticing. They wrote the question in the same order. I'm like, people, authors, can you not get in that groove? Okay, N and SI. N and SI are diagonally related. Same like what they did with atomic size. Okay, let's see. When you have a diagonal relationship, you have to test both trends, right? Left to right, top and bottom. Let's see. If we go from left to right, the one on the right is larger, right, in ionization energy. Okay, so this one here will be larger in ionization energy because the size is smaller. Okay, from top to bottom, Because it's decreasing as we go lower, that means the one that's further up is higher. So both trends show that this N is our answer. So I'll write this up here. N is our answer. Okay, just like before, y'all. I'm telling you, I'm like they got lazy with writing questions. O and CL, OCL, O and CL also have a diagonal relationship, but this is the opposite. Okay, let's see. From left to right, the one further right, which would be Cl, should have the higher ionization energy, right? But from top to bottom, the one that's further up should have the higher ionization energy. Well, the rule we have fell apart. Remember, I told you guys before, the rules in chemistry are to make it easier for us to get the answer without doing the experiment like the the authors or the scientists did. This rule falls apart when you have this arrangement. So we really can't get an answer from the rule alone. So what do? If the rule doesn't work, if rule doesn't work, comma, perform experiment. This is the same thing we did when we're doing the electronic configuration using the periodic table, right? Going from left to right, the sublevel. All these rules are not 100% perfect. There's a certain point where they begin to fall apart. And if it doesn't work, that means we have no choice but to perform the experiment like the people who got the data in the book. Yeah. So when you go to this right here in the table, wait, where's the table? Oh, they say a lot of things, but then they tell you that they counter each other, and it's not obvious which would dominate. So in the end, yeah, go ahead and do an experiment in so many words. Yeah. Okay. Now, let's see why it doesn't just go like this, right? For across the period, from lithium all the way to neon. Why don't we have a straight line? Why do we have something that goes like this and then it goes like this, something like that? Why do we have those little kinks? Okay. So we're going back and saying, remember that in reality, these electrons are in sublevels. Yeah, they're in energy levels, but they're really in sublevels. And stuff happens when the energy level breaks apart into sublevels. Okay. So we're told the general trend, when you look at the overview without looking at every little detail, we're told here if you go across the period, ionization energy increases. That's the general trend. But the exception is when you go from 2A to 3A and from 5A to 6A. So this is us going through the groups, right? 2A to 3A. So what is happening from 2A to 3A? Let's see. 2 periodic table, right? So you know you have 1A, 2A, 3A. These are the group numbers there. So when they say 2A to 3A, I'm going to use period 2 because period 2 has got all these elements. So lithium, beryllium, and then boron. So they're saying that in the periodic table, let me actually write boron on the right side so y'all can see 3A is actually here, more like here, right? So when you go from the left side of the periodic table to the right side, between the S, the cutoff of the S, and when you're going to this part here in the P block, something happens to where the ionization energy does not increase, it actually decreases, right? So from here to here, ionization energy drops slightly. And then they're telling you when you get from 5A to 6A, what's at 5A? Oh, I see the culprit here. So 4A, 5A, 6A, 7A, 8A is somewhere here, but okay. So 5A, let me just write all the elements: carbon, nitrogen, oxygen, fluorine, and then eventually neon. So from 5A to 6A, once again, we see a drop in ionization energy. We expect it to go up, but it goes down. Why is it going down? It has to do with the sublevel. So for us to really explain this, we have to look at what is happening in the degenerate orbitals, okay? So I'm going to skip over here and talk about this, and then I'll go into illustrating what's happening. So we're told here, apparently, Boron has a smaller first ionization energy than beryllium due to the electron position 2p for boron, 2s for beryllium. So going back here, what do we expect? So our right expectation versus the actual expectation. Since the ionization energy increases, expectation is boron will have a higher ionization energy than beryllium. Ooh, let me write it like this. Beryllium. Okay? Expectation. Well, reality, boron, and oh, I mean the first ionization energy. Boron has a smaller first ionization energy than beryllium. Well, how do we explain that? So let's see. We have to look at the number of electrons. So let me provide the number of electrons here. Lithium has 3, beryllium has 4, boron has 5. So we want to place, we're comparing boron to beryllium, right? I should use it in correct order. Beryllium versus boron. Beryllium has got 4 electrons, boron has got 5. So I'm going to be placing these electrons in the sublevels, right? Electronic configuration. So for beryllium, and starting in the order, it's going to be, I'm going to write these in the bottom because my goal is to draw the orbital diagrams. It would be what? 1s2, correct, for the first 2 electrons, and then 2s2 for my second 2 electrons. And together, these make the 4 electrons in beryllium. So let me make sure you guys are seeing what I'm showing you right here. Okay, let me draw this a little lower. For boron, where we have 5 electrons, the first 2 electrons are housed in 1s2 sublevel, right? The next 2 are housed in 2s2. The last electron is housed in 2p. But in 2p, since we're only occupying 1 orbital of the 3 available, that's where the last electron goes, right? So it's 1s2, 2s2, 2p1. So remember, when you as a scientist are trying to remove the electron, you target the last one. It's kind of like, you know, in a job, they usually say if they're going to downsize, we're kind of downsizing electrons here. The last one in, the first one out. Who was hired last? Yeah, you're fired. Okay, something like that. So when we're trying to get rid of the electron, the last one in, the valence electron, first one out, right? So our goal here is to go find the last one that came in as we were drawing this based on all those rules. This is our last electron that came in. Poor electron, we're targeting it. This is our valence electron. In boron, where's our last electron? This one here. Valence electron. Okay, now what they're saying is this valence electron in boron is actually easier to remove. And then this one here is harder to remove. But they expected, because boron has got more electrons and it's a smaller size, it will actually be the opposite, that it will be harder to remove this electron, right? So it's like, okay, there's something more going on than what we see. So the rationale here is, once again, when you draw the orbital diagram, the sublevel diagram, you see more details. If we're to describe boron's electron, in boron, the valence electron, yeah, we know it's in 2p, is unpaired. Okay, so bottom line, we learned that it is easier to remove electrons that are alone, or you can say unpaired. Ooh, if I can spell and write, in an orbital. Okay? Remember, we mentioned this before. Half filled orbitals and full filled orbitals are very stable. What does that mean in our world? If you're trying to disrupt that stability, it will cost you money. It is possible to disrupt it, but it will cost you money. And currency in the world of chemistry is energy. So, half filled orbitals and full filled orbitals cost a lot of energy to disrupt. So when you were removing the electron, yeah, you're disrupting the stability. I mean, the element has reached stability. It's comfortable, right? Has low energy. It has a half filled orbital or full filled orbital. Yeah, you can take out an electron, but when you do that, you disrupt the element. So to remove this electron here will cost you a lot more energy than that. Plus, here's the other thing. If you remove this electron, the new outer layer that becomes this is more stable for the element. So I feel like it will almost even help you to remove that electron. No, nothing personal against the electron, right? It's like if you leave, we become more stable. Okay. Here, if this electron leaves, we become unstable. So this one here costs more to remove than that one. So hopefully you see that way. When we're learning this in school, the first time around, I don't remember when, I just remember it was horrible. Later on, I'm like, man, I gotta bring myself in what's going on, right? So yeah, removal of this one here costs less energy. This one here costs more energy. And so hopefully you see that. The next one is what happens with nitrogen. Now with this one here, nitrogen versus oxygen. So I'm going to be showing you guys once again the difference. It all boils down to what the element wants. Apparently that matters in this conversation here because the element will either fight you and then require you to apply more energy, or it will help you because you're helping it to reach its natural goals. Okay. In the case of nitrogen versus oxygen, this is my chance also to go over the orbital diagram again. So even though it's drawn right here, I'm going to show it to you again. Nitrogen versus oxygen. Now we're looking at group 5A, where they said there's another kink. Group 5A versus 6A. Representative elements we're looking at is nitrogen for 5A, and then 6A is oxygen. So nitrogen has how many electrons? Is it 7? Yep. I have my periodic table here, but then my table is too high, so I have to stand on my tippy toes. Okay, I'm going to write the shorthand configuration so I know how to, yeah, so I don't have to draw all the boxes, right? For nitrogen, that would be what? Helium takes care of 2, shorthand configuration. After helium, I have 2s2, 2p3, okay? Remember the 2s sublevel only has 1 orbital. The p's have 3, right? I'll come back to that. Oxygen, also shorthand configuration. So this kind of, in going through this part, we're kind of remixing a lot of things, right? You have shorthand configuration, you have orbital diagram, and then you have all those rules and everything. Okay, helium takes care of 2 electrons. The 2s sublevel has 1 orbital. 2p has 3 orbitals, 3 boxes. Okay, now I'm going to fill them in. Up, down, right? And then the 2p3, up, up, up. I'm following Hund's rule. And then oxygen, up, down. And then here I got 4, right? Up, up, up. That's 3, 4. Okay. Now you saw the order in which I was drawing them, right? In the order I was drawing, this was the last one I drew. So this is the last one in. This is the valence electron right here. This is the valence electron for nitrogen. Last one in. This is the valence electron for oxygen. So which one is easier to remove? Remember the goal of the element. The goal of the element is to be stable. Once the element has reached stability, it will do a lot to protect that stability it has. So this is half full. right? Half full sublevel. The element likes half full. This one here, we have just went a step above half full. So it it is easier to remove the valence electron from oxygen because the remaining species is a general, if you don't want to say ion or whatever, you just use the term species has a half filled orbital. Okay, so if we remove this electron here, what we leave behind for the oxygen is a preferred state, which is half filled. So the oxygen will not fight you so much on that, because it's like, wait a minute, you're going to help to make my life better, and it's going to cost me one electron, the valence one, the one that came in last. I don't even have that much attachment to it, right? Yeah, you can take it. So you take it, and then now the oxygen has this new status, half filled, more stable. On the other hand, nitrogen is like, wait a minute, you're going to do what? You're going to take away the last electron, the one that's causing me to be stable? No. This one, it will cost you a lot of energy because the nitrogen is already at stability. Okay? So it all boils down to what's happening at that sublevel level. That's why we don't have a straight line, we have them kinks like that. This is you paying the price, right? Paying the price, man. Okay. So here, you want to be familiar with how to answer this question, because once we've gone through all that dialogue, now we're trying to see what's going on here. The one thing you have to know how to do, which you probably have seen in your quizzes and stuff and your homework, is you want to identify what sometimes the identity of the element or the group number of the element by studying the ionization energy. Okay? So here we're told that there are trends in second and successive ionization energies. Of course, remember we said this earlier. The more electrons you try to remove from the same chemical, the same element, the more you pay, because the element is kind of learning along the way, and the more scientific rationale is you're removing electrons that are a lot closer to the nucleus, so there is a higher nuclear charge each time for the remaining electrons. So we're told here the electrons essentially say the ionization energy, they're referring to ionization energy, depend on the number of valence electrons in the element has. Removal of each successive, not the first one, the newer one, electrons, costs more energy. We got that. Why is this the reason? You have shrinkage in size due to having more protons than electrons. Outer electrons are closer to the nucleus, and therefore they are harder to remove. It costs more. And as you're removing electrons, the atom shrinks. It begins to shrink. It's like it's losing weight, right? It's losing electrons, so it's losing size and it's shrinking. So we expect a regular increase in energy for each successive, each future, each additional removal of the valence electron, right? Now, as we're looking at this picture here, we're being told, but note, there is a large increase in energy when core electrons are removed, okay? So all they're saying is once you remove all the valence electrons, there is a large increase in energy when you try to remove core electrons. So let me use this to illustrate what's going on. They're showing us a picture here of sodium. So I'll do sodium. I'm going to go back to Bohr's model once again, because this explains what's going on. With Bohr's model here, actually I'll use a configuration, right? Of we have sodium. Sodium has 11 electrons, right? Sodium atom. They're showing you the first ionization energy. This is the second. It says first, right? In this table here. Let me zoom it in so y'all can see. This is the first one. So it's showing you how much it costs. What's the units here? It didn't say. Oh, sorry, right here. Kilojoules per mole. Okay, it costs 496 kilojoules per mole to remove the first electron. After that, man, the amount is almost 10 times. After that is in the 6,000, almost 7,000. Okay, so we'll see how the ionization energy can tell you what the element is or what group it is in. I'm going to use two illustrations here. One, Bohr's model. Remember, in Bohr's model, you have sodium in the center, or I'll just put the charge. We have plus 11. You have the first energy level, N equal 1. Second energy level, sodium is in what? Energy level 3, so I'm going to use 3. The first 2 electrons are here, 1, 2. The next 8 are energy level 2. 1, 2, 3, 4, 5, 6, 7, 8. This picture may help. I'll use the sub-levels also to show you that. Then we have the last electron, valence electron, on energy level 3, which is, what is it? 3s1, right? That's the valence electron. So they're showing you here, it's easier to remove the valence electron. To remove this electron here, it only costs you 496, okay? Once that electron is gone, you're now trying to remove the electron from the inner energy level. Now you see this energy level here is full, right? So you trying to remove any of these electrons costs you, in this picture here, it shows it costs 10 times the energy previously applied. And why is this the case? You are, okay, so reason, you are trying to remove core electrons. I feel like the picture of Bohr's model helps us to understand core electrons a lot better than even the configuration, right? Because the picture I had before showed you the valence energy level, which was here like this with the 1 electron. Remember, as far as the energy levels are concerned, the last one is the only one called valence. Everything inside, like this one here, in this picture here, this is core and this is core. So only the outer one is called valence electron. All the inner ones are called core electrons, kind of like the skin of the apple, and then the core is the inside. So once the valence electron is gone, the cheapest to remove, what you have to remove next is the core electron. And the core electron costs so much more energy. In this case, it costs 10 times. That's how we know we are removing a core electron, because it costs so much more energy. It's 10 times, 7 times, 5 times. Okay? So using this picture here, I can now relate this to the graph. Man, I wrote all around here. In the graph that they gave us here, because the goal is not for you to look at Bohr's model. The goal is for you to read the graph and understand the energy difference and the significance. I'm going to draw my own graph for sodium so I can write on it. Their graph is okay, but I want to draw my own graph. This is for sodium. I'm going to show here, let me see. Oh, I'm going to show here number of, or I should say electrons removed, not number of. Electrons removed. And then my y-axis will be energy. So I'm going to draw this. You know how they stack this like this? I'm going to do it separately. My first one will be, it goes from 400 to 10,000. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is going to be 10,000 right here. Kilojoules. So this first one is going to be 1,000, right? Obviously 1,000, 1, 2, 3, 4, 5. This is 5,000 right here. So I'm redrawing this picture so it makes more sense to me so I can answer questions. Okay, so for sodium, my first ionization energy was somewhere, it wasn't even at 1,000. Let's say it's like here. This is my first ionization energy. It got this much. This is first ionization energy. Second one, it got to what? 4,000? Second one got to 4,000. So I'll put it somewhere here. Okay. Second ionization energy. Third one got to what? About 7,000. So this is 5,000, 6,000, 7,000. Third one got to this. About this level right here. So what you want to do here is see where you have the greatest jump, right? Looking at my picture here, when I went from the first to the second, this is where I have a times 10 jump. So you separate the one that requires less energy from the one that requires the greatest jump. And then count how many energy levels do you have, or how many energy requirements do you have, or how many electrons do you have. I only have one. So I conclude this element has one valence electron. Okay, so what I'm doing here is showing you how to figure out how many valence electrons are in the element based on the ionization energies provided. Okay, find in the numbers given where you have the biggest jump. Separate the one with the biggest jump from all the electrons before. So this is my first electron, my second electron, this is my third one. The one that has the biggest jump is the second electron. So that means the first electron is the only one in the valence shell. The second one has the biggest jump because the second electron is part of that inner energy level, the core. Okay, so from this I can conclude this element has one valence electron and is therefore in group 1. You can say 1A. Let me do a problem for the second one right here. Is there a question here? No, we're close to the end. Okay, there's no question here, but let's do the second one here. This one here is magnesium. So we got 7, 1400, 7000. I'll do the same thing for magnesium. I'll use the same picture so I don't have to redo this. So for this one here, first electron around, it doesn't even reach 1,000, 700 first electron. Second electron was what, 1400, so it's kind of double. Then third electron was 7,000. So 7,000 something. You have to get it exact, close to 8,000. Okay. In the case of magnesium, which is what I'm looking at right now, where do we see the greatest jump? The greatest jump, as far as energy required to remove electron is concerned, happens between the second and the third. That means the first 2 electrons are the valence electrons. They didn't require as much energy to remove, but the third electron requires way more energy because you're trying to remove the electron from an energy level that is filled and stable. So this element, which is not sodium anymore, we're now looking at magnesium, has 2 valence electrons. They're the cheapest one to remove. They cost us less energy. And this is therefore in group 2A. Okay. So if you've worked on your homework question, you should have a question like this, either homework or quiz, right? You should have a question like this. So if you haven't answered it, or if you did, but you didn't get what you were answering, this is why. This is the reason why. Right? Okay. So it shows you here how you can figure out the ionization energy based on the different elements provided. So you have this list. If you need to refer to it, the list is here. This is showing you the cutoff point. These right here are the valence electrons, the energy required to remove them, right? They're under the zigzag. And the one that jumps so much, the higher one, that's the core electrons. So you see right here, core electrons are these, the energy required to remove them. And then we have valence electrons on the bottom. These are valence electrons. Okay. Finally, I'll let you guys read the characteristics of metals and nonmetals so you can see right here. What I want to talk about is the periodic trend and metallic character. In the periodic trend, we see that, we mentioned this before, most of our periodic table technically has a lot of metals, right? And the zigzag line somewhere here separates the nonmetals that are very few in type, but many in number. As far as the abundance, we have a lot of nonmetal because of human beings and living things. Nonmetals are to the top right mostly, and then metals are everywhere else, bottom left mostly. For that reason, I use that logic to remember metallic character. Since they're here in the top right, if you go from left to right, you're going to see more nonmetals. So our focus here, though, is on metallic character. So metallic character decreases, right? If you go from left to right, because when you go to the right, you see more non-metals, not more metals. So that explains that. You see more non-metals when you go to the right. But when you go to the bottom of the periodic table, metallic character increases. Why? Because that's where you see most of your metals. So if you're going to be seeing more metals, then it increases. So we have essentially talked about this trend right here. Okay, remember, these are your non-metals. All of these are your metals. And then, of course, the purple ones are your metalloids. They have both characteristics. So we're gonna be finishing this slide. I'm gonna start the other one as soon as I get done with this. So we're told here, on the basis of periodic trend, choose the more metallic element from each pair. So I'm going to go with this picture since they already have this in picture form, SN and TE. You look at your periodic table, SN, TE. So in my case, they have a what? SN, TE. In the same period. So they have it right here, SN and TE. And we said more metallic on the left, right? I mean, correct. And then we have more metallic on the bottom. If I can spell metallic. These are all since I've zoomed in, the letters are all smudged together. But anyway, so this one here will be more metallic, SN, right? Because it's further left. And the one that's further right is more non-metallic. So SN should be our answer. And they say it right here. SN is more metallic. Okay, between these two, P and what is this? SB. Once again, have a periodic table that has all the symbols and stuff. Further down is more metallic. So I'll say this one here is more metallic. Because it's a lot closer to the one that is the area that is more metallic. So yeah, we have that more metallic. Feel free to read the extra information. Can you see? I'm not going to say this is lazy. I'm just saying, yo, come on. Deja vu again. Okay, diagonal relationship. GEIN. Remember, the one that's more left and more down is more metallic. So let's see, between IN and GE. IN is further left, so it's more metallic, using the across rule. And top and bottom rule, the group rule, we see that IN once again wins out as being more metallic. It's more metallic. And then this last one, I know. If you're seeing this right now, you're like, that's what I would do. This is how we will respond at home. Yeah, seriously, y'all. Again, okay. So with this one here, if we use the top left right rule, it would say S is more metallic. If we use the top bottom rule, it would say BR is more metallic. Since we can't use the rule falls apart here. As before, we'll perform an experiment. I want to call somebody. No, I'm not calling them. It's not that serious. It's just to illustrate to you, like with every other rules we have, chemistry rules are only useful to a certain point and they begin to fall apart. Okay. And this is essentially the end of this chapter. I'm going to start the next one today because we are running out of time. Does anybody have any questions? Okay. Oh, finally, this downloaded only after so long. Okay, let me go ahead and save this. I have to oh, you know what I realized? I can just stop the recording because there has to be a different recording. Ignore that.